Welcome everyone to the first lecture of my course on the ARC challenge and the basics of program induction. So my name is Fausto Carcassi. I am an assistant professor at the Department of Linguistics at the University of Amsterdam and at the Institute of Logic, Language and Computation. And this course is going to be about the ARC challenge and related topics. It consists of 5 modules. The first one is the introduction. That's the one that you're watching now. Then we're going to have a module on formal tools that are required for doing program induction with a focus on tools that are useful for the ARC challenge. Then we'll cover symbolic search, neural search, and finally, we'll get more specifically into previous approaches to the ARC challenge and how they relate to the content covered in the first 4 modules. Each module consists of a lecture plus a programming lab. You'll find everything on the website, except for module 1, which only has 1 lecture. So what you're looking at right now. This course as a whole is thought mainly as a first introduction to program synthesis and to the variety of approaches that you can take to synthesize programs. And the ARC challenge is more of a case study for seeing what you can do with program synthesis and what are the challenges that it presents. I'll also cover some related approaches which are maybe technically not program synthesis, but still relevant for the ARC challenge. For instance, transduction, which is something that we'll talk more about later. The course is hosted on my website, so you can find it at the link that I put there. You might be seeing this on this website, or maybe you're seeing this on my YouTube channel. So either is fine for watching the lectures, but the labs are going to be available only on the website. So I wanted to start with a bunch of disclaimers to say what this course is not. So first of all, this is not a mathematics course. So often I'll be quite imprecise with things. This is also just a first introduction. So pedagogically, the best approach is not to just present things in their full complexity. If you're interested in some precisification or some details, I might add a couple of them in the YouTube description. So go look there if you have any doubts. Also, feel free to add comments in the YouTube videos or send me feedback on the feedback form on the website if you think that I was imprecise at any point, and then I can fix the material in the course. The second thing I wanted to say is Wittgenstein citation from the Philosophical Investigations, which goes as follows. This is our paradox. No course of action could be determined by a rule, because every course of action can be made out to accord with the rule. The answer is, if everything can be made out to accord with the rule, then it can also be made out to conflict with it. Why am I bringing this up? Well, because this is also not a philosophy course. So I'll mainly be focusing on implementation. Of course, behind all of the concepts that we are going to talk about, there's a lot of philosophical stuff you could say, and people have done so. There's a huge philosophy literature on things like rule following and induction and related topics. I'm basically going to ignore all of that wonderful stuff just for the purpose of giving you a practical course where you can look at how program synthesis works in practice. So you might find this course too easy, in which case I would say this is not the course for you. So I had to pick a level of complexity when designing this, and really I'm starting from scratch. You might also find this too difficult, especially when it comes to maybe the formalism or the level of Python I am assuming. But I'm not explaining things where I think there's already a lot of good explanations easily available online. So if something is not clear, ask ChatGPT, or even better, go and look at YouTube videos where people have explained those things. So if this is too easy, maybe this is just the bit that you're seeing. So maybe try other parts of the course. They might be more interesting, or maybe just listen at 3x, and that might bring the density of the content to a level that you find stimulating. I'll assume familiarity with Python to a large extent. You can get ChatGPT to explain what is not clear. A choice that I made, which might be slightly controversial, is that I decided to devote equal time to symbolic approaches and neural methods. Of course, right this moment, neural methods are more popular. Personally, I really like neurosymbolic methods. And of course, I have to go through the symbolic part of the neurosymbolic. Otherwise, the neurosymbolic doesn't make sense. So if you're really not interested in the symbolic methods, then the course is structured in such a way that you can just skip the module on symbolic search. But I would suggest that you at least skim through it if you don't know that content, because there's a lot of valuable insights in the symbolic approaches that people have developed. So this is the first lecture, which is called just the ARC challenge and program synthesis, and we'll cover the following content. So I'll start with just a little discussion about learning and manipulating representations, and then I'll discuss in very informal terms the François Chollet paper on the measure of intelligence, which kind of laid the theoretical foundations for the ARC challenge. So let's get started. Learning representations from little data. So here's something we can do. If I ask you, what's the next digit of the following strings? And then I say 00011100011, and you're probably thinking 1. Okay, next one. 0011010100010, and you're probably thinking 1. 0001100001100, and you're probably thinking 1. Now, of course, the prosody, so the way that I pronounce those things, might give away a little bit what the pattern I'm thinking of is. But I think even if you would just read these strings without me pronouncing them, you will probably agree with everyone else who's looked at these strings in terms of what the natural continuation is. This is a simple case. You might think it's a simple pattern. In a sense, the space of possible rules that might be happening here that I might have been thinking about when I wrote these strings is not that large. So let me give you another example. What's the next transformation? So let's say we have a function that transforms squirrel into Mr. Squirrel, penguin into Mr. Penguin, and papaya into Dr. Papaya. And then I ask you, okay, what does orange become and what does cat become? If you stop right now and think about it for a second, then you might agree that the most natural transformation here is one that turns orange into Dr. Orange and cat into Mr. Cat. So what is the transformation? Well, there's a variety of transformations that could be happening here, but maybe it's one that transforms animal, anything that is an animal, into Mr. Animal, and a fruit into Dr. Fruit. Note, this is quite impressive because, as opposed to the first example, here the rule really comes out of the blue. There's nothing on the screen that tells you that the relevant distinction here is between animals and fruits. And yet, that's where your mind goes naturally when you look at the examples of transformations. So we seem to be able to do this with just very, very few examples. In fact, here in the examples of the transformation, you only have one example with a fruit, and then you draw this wild generalization based on the amount of data you have, that is nonetheless probably fairly universal. Everybody, well, vast majority of people, I think, are going to end up with the same generalization. So the lesson here is a pretty obvious one, maybe, which is that humans can learn a huge amount from a single instance, and it's not just when it comes to language. For instance, here's a wonderful illustration of this from a paper by Lake et al. From 2015. You just have this one instance of a category, which is the one that you're seeing on the screen. Just based on this one instance, you can do a big variety of things. For instance, you can classify new examples. So you can pick each of the objects on the screen here and say whether it belongs to the same category as the example of the unknown category that that you can see on the left. You can generate new examples. For instance, based on this instance, you can generate examples that probably belong to the same category by varying various aspects of the object. You can parse the object into parts. For instance, you can say, well, this object has two wheels, it has the bit where you stand, it has a kind of trunk, it has the bit that you hold, and people would probably parse the object quite similarly. And you can also generate new concepts. For instance, you can merge this example that I gave you of, or that Lake has given us of a novel category, and merge it with well-known examples, well-known concepts that you already have into something new. For instance, this rather ridiculous locomotion device, that's maybe the kind of stuff you would see people go around in San Francisco. So sometimes we cannot actually generalize very efficiently, but we still seem to enjoy the process. For instance, there's Roger Price's doodles, which are squares with little illustrations, very minimalistic, often with a humorous explanation. So you're supposed to describe what you're seeing here in the picture. And the solution for this doodle, well, Price proposes two solutions. 4 elephants examine an orange, or dead point position by a billiard game. So both of these are funny. They are not what you would think when you first see the image, but somehow the fact that you can kind of see a meaning into the image after seeing the description is something that we find very enjoyable. So we don't just have a skill for massively generalizing from very little data. We seem to also take aesthetic pleasure from fitting patterns into sparse data. So we're not only good at it, we also enjoy it. How do we do this? Well, what we are doing must be something like inferring a rule or a structured representation. The representation might, for instance, encode a piece of the world, like in the doodle case, or maybe it's solving a certain task. So there's a variety of things that the representation can do. But what we do is we use data very efficiently. Unlike neural networks, at least in their naive usage, we only need a few or even just one example. So the mind, if it finds such a rule or a structured representation, it must search for it in somehow. And that's quite impressive because, as we will see later, searching and finding a good representation to fit data is very hard. especially in open-ended settings. It feels crucial to our intelligence that we can do this, and specifically that we can do this with just a few examples in seemingly open-ended settings. Program synthesis, which is the main topic of this course, is one way or one family of approaches for doing this, for searching and finding for a good structured representation or rule based on some data. And this learning happens explicitly, so you find in program synthesis a program written in a specific programming language that encodes the rule or structured representation. As opposed to other methods, which we'll also discuss, though not in as much detail, for finding rules in a more implicit format. So the terminology around program induction or program synthesis is extremely messy. People have called it in many different ways, and the meaning of each of these terms has changed over time. You can hear it being referred to as program induction, program synthesis, inductive programming, church problem, programming by example, and so on and so forth. These are not exactly the same thing, but they are kind of a whole cloud of different, slightly varying approaches. The general idea is to produce a program in a programming language that satisfies some specification. The specification itself can take many forms. For instance, it can be, which is going to be our main focus, examples of the rule, but it can also be a trace left by the program. It can be a partial program that you're supposed to fill according to some specifications, as well as anything anything that a program generates or that becomes visible can be a specification for a program synthesis algorithm. What we will care about is programming by example. So what does that mean? Well, you observe some examples of tuples of input to the program and output of the program, and you infer some program such that when the program takes that input, it returns that output. And you can use this function or program that you found in a variety of ways. For instance, you can apply it to new inputs and get new outputs. Program synthesis, as I've already mentioned, also has an implicit counterpart, where, for instance, the program is encoded in the weights of a neural network. For instance, one example of many of this is differentiable neural computers, but of course also transformers, any neural architecture you can see also in this slide. ARC is sometimes described as a program synthesis benchmark. This is not the only way to see it, but it is the view that I will take in this course. So this leads us into a paper by François Chollet on the measure of intelligence. I want to start here one step before, or several steps, I guess, historically before the paper, with a citation by William James from Principles of Psychology, the first chapter. And it is by now become a kind of classic citation. People actually don't quite cite the correct version, well, the original version as formulated by William James. So if you just Control F what people usually cite, it doesn't show up in Principles of Psychology. And so I went and found what I think is the most likely source for this. And I'm going to read the whole thing because, well, it's hard to beat William James when it comes to prose. Suppose a living frog in the position in which we placed our bubbles of air, namely at the bottom of a jar of water. The want of breath will soon make him also long to rejoin the mother atmosphere, and he will take the shortest path to his end by swimming straight upwards. But if a jar full of water be inverted over him, he will not, like the bubbles, perpetually press his nose against the unyielding roof, but will restlessly explore the neighborhood until by redescending again he has discovered a path around its brim to the goal of his desires. Again, the fixed end by varying means. And so this last bit, the fixed end by varying means, is probably what people kind of incorrectly cite when they say intelligence is achieving one goal by varying means. Then James goes on to say, the pursuance of future ends and the choice of means of their attainment are thus the mark and criterion of the presence of mentality in a phenomenon. We all use this test to discriminate between an intelligent and a mechanical performance. We impute no mentality to sticks and stones because they never seem to move for the sake of anything, but always when pushed and then indifferently and with no sign of choice. So we unhesitatingly call them senseless. This is just wonderful, wonderful writing. All of William James reads like this. So if you've never read William James, go for it. It's really worth it, especially in the varieties of religious experience. But Principles of Psychology is also excellent. So one thing that I think people slightly, one way in which I think people slightly misinterpret perhaps William James is that they take this famous citation to be implying that William James thinks that the variety through which you achieve means is a measure of intelligence, but in fact, that's not what William James is saying here. He's saying mark and criterion. He's saying discriminate between an intelligent and a mechanical performance. He's using this as a way of determining whether something has intelligence, not how much intelligence it has. So if we want to find out how intelligent a system is, then this is not going to do, at least for William James, but I think he knew what he was doing when he wrote mark and criterion rather than a measure of intelligence. So the problem, of course, is not solved here by William James. We need something more. And many approaches have been proposed to measure intelligence. For instance, a famous example is Raven's progressive matrices. The way that they work is you have a grid of objects, and then you have to complete it. This is from 1936. It has become a very famous measure of intelligence in humans. Another example is Bongard problems. This came much later, from 1967, published then in 1970. And the way that they work is you have 6 examples of objects that satisfy some property, and then 6 examples of objects that don't. And what you need to do when solving Bongard problems is describe the rule for inclusion in the category in English. So all of this was quite popular. But then our story really begins much more recently. And the setting of our story was this enormous explosion of AI systems from around 2018, but of course it really took off in 2023 with the release of ChatGPT. Surprisingly, our story begins slightly before ChatGPT, towards the end of 2019, when François Chollet publishes this paper on the measure of intelligence, which is kind of the first theoretical exploration of the foundations behind the ARC challenge. And that's when things kind of took off for us. So what does Chollet say in this paper? Well, he starts with a citation by Legenhatter 2007. Intelligence measures an agent's ability to achieve goals in a wide range of environments. This, of course, echoes to some extent William James's definition of the criterion for intelligence. But of course, this is in terms of measures rather than just a criterion. And it's in terms of goals and the variety of environments rather than goals and a variety of means. Cholet decomposes this definition into two parts that he emphasizes distinctly. So he says, first part is that of achieving goals. So you have a task-specific skills. And here there's echoes of Marvin Minsky in '86, who writes, AI is the science of making machines capable of performing tasks that would require intelligence if done by humans. So the idea here of Minsky, and also the idea of this partial component of this definition of how to measure intelligence, is that we should look at task performance. So how good are the machines at specific tasks that humans can also do? Then there's the other side of the definition, which is about generality and adaptation. So the bit that says in a wide range of environments. And here there's echoes of Turing in 1950, who says, presumably the child brain is something like a notebook, as one buys it from the stationers, rather little mechanism and lots of blank sheets. So what we get is a bipartite definition of intelligence. And each of these parts has been has a long tradition of approaches. So the skill-based evaluation, so what we would think of as measuring intelligence by how well it achieves goals. There's many approaches for doing this. One approach is human review. So some human judges observe the model's input-output and see how good it is at solving the task. That will be, for instance, Turing test style. Well, it's not exactly that, but it's close enough for now. Then you have something like a white box analysis. If your model is interpretable, you can just look inside the model's implementation and check what the skills of this model are. You can do optimality proofs, for instance. Then you have peer confrontation, so a system that competes directly against other AI or humans, and that's how you find out how skillful it is. Chess machines are a typical example of this. And then you have benchmarks. So you have a system that produces outputs for a test set of inputs or environments, depending, for which the desired outcome is known, and then you score the response. And that will be really most modern evaluations. This is now the default approach for evaluating how skillful a system is. The question that's relevant here is this part of the definition of a measure of intelligence enough? Can skill alone be a measure of intelligence? And here, Cholet makes a very nice point. Well, at least it's very nicely phrased in the paper, where he says that the answer to this is no. And that's because so it might be tempting to say yes, and that's because of a slight confusion here. Just because skill follows from intelligence in humans, it doesn't mean that it does so in other systems. So there's a slight kind of anthropomorphization of these systems in assuming that skill is a sign of intelligence because it is so in humans. But it need not be for an artificial system because there are other ways to become skillful beside intelligence. For instance, brute force with simple heuristics might be enough to perform very well in a certain task without being intelligent. So the cognitive skills that are required of a human when performing at a certain level of success in a task might be different than the ones required by an artificial system, because you're removing the kind of cognitive constraints that humans work under. Then we have the other side of the definition, which is in a wide range of environment. This is the approach that's generally taken in human psychometrics. I have my problems with psychometrics, but I think this is not the place to go through them. I'll put some things that you might find interesting in the YouTube comment section. But for now, let's just focus on what Cholet says about this. So this is the general picture that we are working under in psychometrics. You have this general intelligent measure, which G, this faculty that allows for extreme generalization. And you can kind of break it down into broad cognitive abilities, each one of which allows for broad generalization, which again breaks down into specific tasks that you can do well in if you have these cognitive abilities. And each task is a small local generalization, or perhaps no generalization at all. So the good thing about this style of measure of intelligence is that you have standards regarding reliability, validity, standardization, freedom from bias, perhaps. So you can be kind of rather precise in these respects, and then whether the tests we actually have really pass these precise tests. Maybe that's a more complicated question. You can also measure abilities rather than specific skills. So you can target this kind of broad cognitive abilities with these psychometric tests. And you can test systems on a whole battery of tasks, which then allows for inference about their broader abilities. One thing that's possible and it's good, and that will also come up when discussing the ARC challenge, is that the solution to the tasks might be unknown to the AI, but importantly, they also should be unknown to the developers of the AI, such that they basically cannot build in the answer or the specifics of the skill required, which means that the AI, in order to do well at the battery of tasks, will need to be able to generalize from just the little data available, for instance, in the instructions for the task. So, given all of this previous work, Cholet offers a kind of very nice definition of a measure of intelligence, which goes as follows. So the intelligence of a system is a measure of its skill acquisition efficiency over a scope of tasks with respect to priors, experience, and generalization difficulty. And this is the illustration that Cholet uses to show what he has in mind. So you have an intelligent system, and the intelligent system might be confronted with a task. And when that happens, the intelligent system produces a kind of little program. It generates a skill program that can then respond to the task appropriately and perhaps solve it and get feedback back from the task and react to the task in various ways. And then out of this process comes a score for the quality of the generation of the intelligence system, which we can use to kind of assess and measure its intelligence. So a high intelligence system is one capable of making highly efficient use of all of the information it has at its disposal to cover as much ground as possible in unknown parts of the situation space. So this definition kind of nicely ties together the two components of the intelligence, where you have the variety of tasks that it can solve by generation of skill programs, and the quality of the tasks, so how well each skill program performs on the task, and also how efficiently it does so. Okay, So Cholet proposes ARC as a benchmark of general artificial intelligence. So he has this view of how we should measure intelligence, and he proposes ARC as a benchmark of our general artificial intelligence under this measure of intelligence. It's approachable by both human and machines. Ideally, what you want is you want tasks which are easy for humans, which we know have a high level of intelligence, and difficult for current machines, so that you can keep pushing for that gap to close. So as long as there are tasks which are easy for humans, hard for machines, then presumably we don't have artificial intelligence in this strict sense. Tasks are unknown by the developer of the AI system. So as we will see, the ARC tasks are private, at least the ones that the success of the system is evaluated on. ARC targets broad generalization rather than singular tasks. We will see that even though the domain is very well defined, the variety of rules that can be encoded within it is extremely broad. The tasks are also fixed in terms of the data that they give to the system in order to generate a program that solves them. So as we will see later, you have 3 examples of solutions for the task on average across the ARC dataset. The priors for the system to generate the skill programs are given explicitly in advance. They are given to some extent informally. So they are not formally specified, but nonetheless, the ARC team has invested quite a lot of work into kind of trying detailing them. And so here finally is an example of an ARC task. So each ARC task consists of a few examples, and each example consists of an input grid and an output grid. And the input grid is transformed into the output grid with a rule that is fixed for all of the examples. And then you have an input grid for which you have no output. And the task consists in finding an output that, according to the same rule that generated the inputs, to the same rule that generated the examples that you saw for the task. So this is all good, but in what sense is ARC a program synthesis benchmark? Well, a very natural way to solve ARC tasks is to find for each task an explicit grid transformation rule. So this little program, this skill, task-specific skill that the general intelligent artificial system produces can be an explicit program. So any rule that you care about can be encoded as a program in an appropriate language. So the idea, the framing of ARC as a program synthesis challenge or benchmark is that you see these examples of a rule. Here, for instance, you see that this input is transformed into this output, and the same for the other 3 examples. You can probably already see what the solution is. And given these examples, you want a system which generates this skill program that solves the task. And it does so by synthesizing an explicit program written in a programming language, here, for instance, in Python. And then what you get now that you have this skill program is a test input, and you run the input through the program, and you get a test output. An easy way to misunderstand the ARC challenge is that you think, well, here we are just This is basically a visual reasoning. But it is not, because a system that only had in a strict sense could only do visual reasoning cannot solve many ARC tasks. You need further things. So often you need some form of kind of abstract reasoning to solve ARC tasks. Things that have to do, for instance, with the number of objects or the topology and so on and so forth. So this is all good and well. Where are we with the ARC tasks? So let's do a little bit of ARC history. So what this plot shows is the years since a benchmark has been introduced. And on the x-axis and on the y-axis, you have the score relative to human capabilities. And what you see is that for a variety of benchmarks, within just a few years, we got to human level and beyond. Whereas with the ARC challenge, we've really seen quite slow progress for quite a few years. I think 4 years in, they introduced the ARC price, which really gives a strong monetary incentive, and in fact might be the reason why you're watching this video in the first place. And there we saw a massive increase in performance compared to humans. And more recently, so in the 2024 edition, we've seen a really big jump in the performance to the point where, at least many people have been saying, ARC has been solved. So O3 got human performance. Let's all call it a day and go home. So how should we interpret this? It's obviously not as easy as that. The important point here is that O3 and other LLM solutions, we'll talk more about this when we talk about neural approaches to ARC, got high accuracy in the semi-private, not in the private test set. So the ARC price, and really the ARC challenge, strictly speaking, concerns only the private test set. We'll come back to this in the last lecture, where I describe more in detail how the ARC challenge is actually structured. When it comes to actually interpreting, what does it mean that O3 got such a high score in the semi-private set? Well, according to some, for instance, Melanie Mitchell, this solution is not really in the spirit of the ARC challenge. So she has this kind of rather nice blue sky post. If you're following the OpenAI O3 announcements and are curious about the ARC-AGI benchmark and why I think solving this task by brute force compute defeats the original purpose, here are some of the past posts about this from the Substack. It's a very nice Substack post, so I would read it. Well, I have read it. I recommend that you read it. Of course, it's not just brute force compute, it's massive heuristic search. Still defeats original purpose, in my opinion. So she's taking a kind of very definite position. It's one that I'm sympathetic with. Read the blog post for more. But it's not obvious whether the solution that we have seen from big LLMs are in the spirit of the ARC challenge or not. And so notably, LLM strategies usually fine-tune on ARC tasks and or they exploit massive test time computation. So they sample a huge amount of alternative solutions. Maybe that's how people are doing it, maybe not. So I think that's still really up for debate. The reason why I think this is still very interesting is that they kind of shine light on a different perspective on the ARC challenge, which is maybe not the the original spirit of the ARC challenge, but is nonetheless, I think, a very interesting perspective, which I think can be really summarized in the question, how can we leverage the computation we have for the ARC challenge? This was not at all obvious when the ARC challenge was launched. So you have a bunch of computation, but the computation doesn't help you very much if you just have 3 examples of the task, or at least it took a very long time to start to understand how this computation helps you. So now we are really starting to see how the computation can help you. And I think this is a really interesting twist. And one of the ways in which the ARC challenge is really producing a lot of original ideas, which we will come back to in the last lecture. So there's 2 spirits kind of emerging, I think, 2 kinds of approaches emerging from the ARC challenge. How do we use the compute to increase accuracy? So how do we make all of this compute that we have bear on achieving high accuracy? And then the other approach is, well, suppose that we don't just go for increased compute, how do we make it bear on the accuracy, but rather we kind of get creative and we try and find new approaches that actually don't need that much compute. And both are kind of being pursued independently as approaches to the ARC challenge. And this is a little bit a microcosm of the field as a whole. And this is one way in which I think the ARC challenge really is proving to be kind of revealing of the field of AI as a whole. So how will we approach the ARC challenge and program synthesis in this course? Well, I'm structuring it around the questions that you might have when developing a system for solving the ARC challenge, or really for doing program synthesis in general. So one question that you might have is, what language do I want to write my programs in? Is it domain specific or is it open-ended? And this is going to be the topic of lecture 2. So we'll discuss formal ways of specifying a language. And then another question you might have is, how does this system search for a program given a language? So suppose that you have a language, you get some inputs, you still have to find a program written in this language that fits those examples. And that will be the topic of lectures 3 and 4 and the corresponding labs. And then finally, if you want to develop a system for solving ARC or your own attempt, you might want to know what people have tried so far, what's the state of the art in terms of the approaches. And that's going to be the topic of the last lecture. Of course, in order to make this course even just a little bit robust against new developments, I'm not gonna emphasize ARC-specific tools too much. Otherwise, 2025 comes about, and all of these things that I talked about in the course are just completely useless. So lectures 2, 3, and 4, I hope, are going to be interesting and valuable for at least a few years to come. Lecture 5 might not, and the course might also become longer as new approaches are published, and there's more to say about the ARC-specific solutions. So that's it for this lecture. This module only has the lecture, so the next step in following this course is going to be to watch the next lecture and do the corresponding lab. I would suggest that you first watch the lecture and then do the lab, because the material in the lab relies on the material in the lecture. But if you have some background, you might already want to skip to the lab. So I hope you found this useful, and I'll see you in the next lecture.